Welcome to the second part of graphs. Last week you got a lot of the definitions, what a graph is, vertexes, edges, how they're put together, how you may store them, how to traverse them. Now we're going to look at a couple of different applications. We're going to look at networks that, a form of graphs called a network, which basically each of the edges are weighted. And then some applications that use that weighted graph to do things. So we're going to look at a couple things. We're going to look at a minimum spanning tree and a shortest path algorithm. But I want to let you understand at least what a spanning tree is. A spanning tree is just a tree that connects all vertices on a graph. So just so you got that term, so when somebody says, "Oh, I want to do a spanning tree," or if you're in networking, you may have heard a spanning tree protocol. Basically, it's just saying I'm trying to connect all the vertices together in a graph. I just want to have some kind of structure around that. Well, minimum spanning tree is, because I got a weighted graph, now I want to make sure I have all the vertices connected, but I want to do it in such a way that is the cheapest way to do it, or the less expensive, or the minimum weight. And then we'll talk about the shortest path algorithm. Back in the early 60s, and maybe mid 60s, Dijkstra wrote an algorithm to find the shortest path between any two nodes. So we're going to go through those two examples, and then I'll let you do some homework in it. So let's look at the minimum spanning tree. Now, property of a minimum spanning tree is every vertex is included. Nothing's excluded, everything's included. And the total weight of the spanning tree is the minimum possible that includes a path between any two vertices. So it's A to C, whatever the case may be. Now, how would you store that? More than likely, I would do it with an adjacency list, only because it's the most flexible. And your basic algorithm, and granted, the algorithm in here is probably, looks like 2 pages long, but conceptually, basically is you got a starting point, you're going to add a vertex, and you're going to go through all the edges that are connected to that vertex, and you're going to insert the one with the minimum weight. So if you looked at a network like this, which has cities A through F, and maybe those are mileages between them, that would be a network. That I would put those in a matrix similar to, here's, you got two different forms, your adjacency matrix or the adjacency list. I just like the adjacency list, maybe because it's the linked list part of it, less storage space. So granted, if I have to add a node and stuff, it becomes others. But usually how many times do new towns pop up for Google? You're doing Google Maps. So the vertices probably don't change as often. Now the edges change a lot, and those are easily added and subtracted in. But so those are just some of the ways you could store a graph. And then if we look at, okay, now let's look at how do we use these minimum spanning trees. So let's use an easier example. Again, you got your 6 vertices and edges with weights on each one. And the process is, like, if I want to start with A, what do I want to do? I want to insert A, and then I want to look at the 2 edges that are attached to A, and I'm only going to put in the edge with the minimum cost. So, whoops, wrong way. I start with A, and then I looked at, because you saw here I got 6 and 3. I want to put in the 3. So now I'm going to say, okay, now I'm going to go to C and say, okay, now what's the best? Because the purpose is not to get the best route. It's to say I want to make sure I connect all the vertices together at the least cost. So now I'm going to go to C and say, what are my least cost at C? So I look at C, and I've got 3 and 3 and 4 and 2. Okay, 2 is the minimum cost. So now you added C. So I got 3, B. Now I go to, you say, okay, now I want to add in vertex D. Now in vertex D, you've got several different options here, don't you? I can go 3, I can go 2 to 5, 4 to 6. There's a couple of different ways of doing this. So in this case, the cheapest way to get there is taking this link here. So I add this link to include D. Now you go, how do I get to the next vertex? E. I look at the cheapest one, because I could have got 3, 3, 2. Again, you're choosing the cheapest. And when you look at F, whoops, I'm looking for the cheapest. So even though, so it doesn't say I've got to go sequentially, A, B, C, D, E. It just so happened up until I got to this point, because now when I'm adding D, added D, so I want to put F in, so I had a couple of different choices. Could have gone straight here. If I would have gone numerically sequenced or alphabetical, I could have gone this way, but it doesn't have the minimum cost from D to F. So if I wanted to go to E to F, so to get F in this loop, what's the cheapest way to do it? The cheapest link for F is 3. So you add the length 3. So that minimum spanning tree, to get all 6 vertices in, these are the cheapest links to connect, to add that the vertex to the tree. And then if you wanted to get from point A to point B, then you can easily calculate, how to get, if I wanted to go to A to F. So I'm going to do 3, 3, 3 are my ways to get there. So, and for completeness, usually they indicate that these are the ones that were not added to the next. So that would be your final tree. Those links were not added to the spanning tree. So let's take a look at something a little bit different. And you can look at the algorithm, and like I said, as you go through what kind of type of structure was held, but the algorithm itself is fairly complicated. Not a matter of complicated, but it's a matter of looping through to double check if you have everything included. And do you have the minimum path? So you're doing a lot of checking to do this. Now, if you were in networking and you connected a switch, it takes about 50 seconds for a switch to make sure it's ready to go. And in that process, what it's doing this spanning tree. It's going through and saying, who's all connected to me? And because what you don't want in a switch is having that loop. We talked a little bit about last week. I don't want to have a cycle or a loop in my network, because I'm going to waste, I could get myself in an infinite loop. And some of you in your programs probably have run into that maybe once or twice. Believe me, you've stayed in the programming long enough, you're going to do it a lot more. But, so the switch goes through and does that to verify it. So what it's doing is checking, do I have the minimum tree, and I got to make sure I don't have any loops in it. So you can go through the algorithm itself and figure out what you know about it. But basically, I think if you just think of what's the purpose? I'm going to add a vertex, and I'm going to loop through all edges, and I'm going to insert only the minimum weight. So everything else doesn't get included. So now the next one is, how about a shortest path? How do I create a structure or a data structure that guarantees me the minimum, the shortest path between any 2 nodes? So it's similar to the spanning tree. You're going to insert the first node into the tree. You're going to examine all the paths of the adjacencies, and you're going to select the minimum cost. But what you're going to do is you're going to keep doing that until every vertex in the tree, we have what's the cheapest cost to get to every single node. So how do I get from what's cheapest go to A to B? Because the cheapest go to A to B is not a direct shot from, A to B. It's actually C, then to B. So it's finding that shortest path. So I'm going to use that same spanning tree graph. So as we go through the example here, I'm going to start with A, and I'm going to compare, what's the cost between A and C. total cost, that's what that T is. The total cost to get from here to here is 3. Total cost to get to A to B, it's 6. So far, so good. Now when I've got those costs, I'm going to choose that one, but I'm going to insert, now I'm going to insert C, and now I want to look at all the possibilities. What are the total costs to get to C? Well, now, so C, I've got what? Multiple links. So I got 2, and the cost to get from A, because you think I'm always going from a particular source. So the cost to go from A to B through C, I got the total cost 3 here, plus that gives me 2, so it gives me a total cost of 5. C could also go to D, which then would give me, add a 3 there, would be, from A to D would be 3 from A to C and 3 from C to D. And cost to E would be, adding the 4 gives you a total cost of 7. So what am I going to add? I'm going to add my minimum cost is going to, I got total cost C is T5, so I'm going to go A, C to B, add that because that was the cheapest cost. Now I look at that, the vertex B, and say, okay, who's connected to V? Well, C is, we already covered that, and D. So we had a cost there. So now you just got to look at B, but I can also get to D how? I'm looking at D, but I can also get it through 2 ways, right? If you look at this, I can get to D from either from B or from C. So I'm adding D to the network. I look at the minimum cost and which one I'm going to add. Based on minimum cost, I'm going to add the one from C to D, not from B to D, because it is the minimum cost. And I'm going to go through each of these so that I have a list going from each of the different nodes. And you're going to proceed to go through this every single time. So it kind of, let me think here. We'll let you go through the algorithm that's in there because, again, it's fairly long. And that's just your graph for the homework. But if we look at, let me go back here, and we'll let you animate, just see. You can play with this on your own time, but just wanted to see just let you visualize what's happening. Let me see if I can find a smaller graph. They got the same number of nodes. It doesn't make any difference. So you always, with Dijkstra, you're always given a starting point. I'm going to say we'll start from node 3. So I'm going to say, give me the shortest path to all of the nodes from 3 to everything else. And as you run this, and it's just interesting to see how you're going to make sure. I'm going to go through and double check every single link and say, do I have a path? Do I not have a path? What's the cost between each of the links? So go through, and once you see this thing run, and what I think I'll do is speed it up. So all it's doing is going through each node, checking the cost of the links, and then updating the cost to get from each of the different nodes. Once it's gone through and updated all the costs, and then it's going to come back and say, okay, what's the paths? Now that I understand the cost between everything, then it's going to go through and say, what's the path to get from point A to point B, to get from 3 to every other node. Just give it a second here to, I'll do here, just kind of speed that up so we can kind of see. I probably should have given you a directed graph, would have been a little bit quicker. But it's saying from every node, starting from 3, what's the shortest path to get to each one. So play around with this, see what, I think you'll find it very interesting. Slow it down, speed it up. But hopefully this gives you a rough idea of minimum spanning tree and Dijkstra's algorithm on shortest path. And I made the chapter work a little bit less complicated, so hopefully that'll work for you too. If you have any questions, give me a call. Thanks.